gate, it's inverted, so any 1 in gives you a 0 out, and 2 zeros in gives you a 1 out. You just simply have to memorize these, unfortunately. You have the Boolean identities. You have 19 Boolean identities, and again, these are identities that you just need to remember. I'm not sure if they're in the actual handout that they give you. You do get a handout with the FE exam, but I would suggest that you just memorize these. So here on the first one, you have 0 is ANDed with A, and remember in an AND gate, an AND truth table, you must have both 1s in to get a 1 out. So if 0 is ANDed with A, then you're going to get a 0 out. The second one is 0 ORed with A. So in this example, any 1 in will give you a 1 out. So if you're ORing this with 0, whatever A equals will be the result. So if A is equal to 0, then 0 ORed with 0 equals 0, but A was equal to 0, so it always equals A. So you can use these to simplify expressions. 1 ANDed with A equals A. So again, you need 2 1s in to give you a 1 out on an AND gate. So you've got a 1 already, so 1 ANDed with A. If A equals 0, the output will be 0, which is A. If A equals 1, then 1 ANDed with 1 equals a 1, and again, A was a 1, so you get A's result. This is sometimes called masking an input. 1 ORed with A always equals 1. That makes sense. A ANDed with A equals A. So if you've got a 0 ANDed with a 0, that's going to equal 0. So they're both equal to 0. A 1 ANDed with 1, 2 1s in give you a 1 out, so it's always equal to A. So if you see an expression where you have A ANDed with A, you can just simply simplify that to just an A. Or if you have an A ORed with A, you can simplify that to an A. If you have A ANDed with not A, you can simplify that to make it a 0. If you have A ORed with not A, you can simplify that to a 1. So you can see these different examples. They get a little bit more complex, but you'll see we'll use a few of these examples, and then we'll use them in the RS Logix software as well. So we're going to prove the identity 0 ANDed with A equals 0. So in this example, we have A and B is set to 0. So in our truth table, we have A can be 0 or a 1, B can only be a 0. So you're always going to get 0 out because it takes 2 1s to get a 1 out. So that's true. This identity has been proven, both with the logical gate and the truth table. Prove the following identity. A ORed with A ANDed with B equals A. So here you have A is ANDed with B. This is the AND gate. The result is Y. And then Y is ORed with A. So this is Y in this example. Y is ORed with A. And that gives you the result F. So in this example, if this proves to be true, whatever A is will equal F. So we have A 0 0 0 1 1 0 1 1 is ANDed together to give you Y. So that's any 1 in or both 1s in give you a 1 out. So 0 0 0 0 1 is a 0, 1 0 is a 0, and 1 1 is a 1. And then we OR these together. So that's this result ORed with A. So we have 0 0 is equal to 0. 0 0 equals to 0, because now we have to take the result of this truth table and put it right here, and so then we'll have and then we take the result of A, because A is going to equal this, so it's 0 0 1 1. So when they're OR together, any 1 in gives us a 1 out. So 0 0 equals 0, 0 0 equals 0, 1 0 equals a 1, and a 1 1 equals a 1. So you can see F equals A. So that is again true. That identity has been proven. So if you see the logic A ORed with A and B, you can simplify that just to A. Next, let's prove this truth table. We have A is ORed with B, ANDed with A ORed with C. Is that true? A ORed with B, ANDed with C. So here we have A ORed with B. There's your OR gate, A and B. We have A ORed with C. A is ORed with C. We take the results and we AND them together, and that equals F. So actually, I'm only proving half of this identity. I'm proving this identity here, and this will be left up to you to prove this identity here. And if they're equal, then it's true. So here we have A is ORed with B. The result is Y. Then we have A is ORed with C. The result is Z. Then we have Y is ANDed with Z. The result is F. So this, again, you go 0, 0, 0, 1, 1, 0, 1, 1, and then or any one in gives you a 1 out, and then again 0, 0, 1, 0, 1, 1, 0, 1, 1. Any one in gives you a 1 out. So you take the result of this and the result of this, and you put them here, and then you AND them together, and you must have all ones in to give you a 1 out. This is where Boolean logic comes in handy. You can simplify these large statements here. So here we have WXY not Z, ORed with WX not Y not Z, ORed with WX not X, Y not Z, ORed with WX not X, not Y, not Z. These are actually ANDed together. WX, Y, and not Z in this example are ANDed together. So when you look at these, find out the common things here. So you have WX not Z, WX not Z. So you can group these two together. So you can say WX not Z is ANDed with Y ORed with not or not Y. So again, that's Boolean identity 14 allows you to do that. So here we have W not X not Z is again ANDed with Y ORed with not Y. So we can, these become ones, so we're left with WX not Z plus WX not X not Z. So then we again simplify, we see the common digits there, W and not Z, and W and not Z. So we have W not Z ANDed with X ORed with not X. And again, this becomes a 1. So we're left with W not Z. So if you had a logic diagram and you had this gates right here, if you wrote it into Boolean expressions and simplified it, you'd come up with this. So if you were actually hardwiring your gates, this was very important to reduce the number of gates because it reduced the your cost of your product. So it's very important to understand the Boolean identities. Next, we're going to identify PLC system components, selecting your PLC. When identifying your system, you need to consider the following. What are your communication requirements? What are your physical I/O requirements? What is your cost? How much money do you have in this budget? And your physical size limitations. So let's first talk about the communication requirements. Do you need to talk to any DCS, a distributed control system, or another computer? And if you do need to talk to that other system, what type of communication protocol do you need? Do you need a Modbus communication protocol? We're not really talking about this at this course, but it's important that you do understand that there are different communication requirements, and it requires different hardware to satisfy and different programming skills to satisfy these communication requirements. Your physical I/O requirements. We'll look at this in more detail later, but basically what you do is you count all of your inputs, your discrete inputs. If it's a switch or if it's a push button, that's a discrete input, so you only need a it's either a 1 or a 0. If it's a temperature switch, that's also a discrete input. If it's a tank level and you've got an analog signal, so you've got your tank level converted to a 4 to 20 milliamp signal, then that's an analog signal, so you would need an analog input card. And then you want to count all your outputs. What are you trying to turn on, or what signals are you sending to your customer's computer system if they're hardwired or an analog signal? So if you wanted in this example to give them the results of the alarm, so you've gone through and you've created this logic and you're looking at all these different alarm signals, and you want to send them a common signal out that says that, hey, this system is either running or it's in an alarm state. So that would give you 2 discrete outputs. So you need to sum up all these inputs and outputs, and then you count them all, and then you can kind of build your system from there. Now so that's your physical I/O requirements, the cost. Different PLCs cost different amounts of money, and there's a big swing in the cost. So you want to understand how much money you have in the budget before you actually decide what system you want to use. Also, different PLCs are physically different sizes, so you want to make sure that you have, given your physical limitations, you want to make sure you pick the right processor. The Allen Bradley offers numerous PLC options. You have the Pico, which is a very small relay replacement. The nice thing about the Pico software is it is free, and the simulation software is free. So I encourage you to go to the supplementary CD. You'll see in there AB pick a Pico software, and you can actually run that software link, and you'll have the software, and you can actually play with it and look at the demonstrations and go through the help screens and what have you. The MicroLogix 1000, 1100, 1200, and 1500 unfortunately require the RS Logix 500 software, and it can vary from $1,800, and that's the full version, or you can buy the starter kit, which is only about $500, but the starter kit can only be used on the MicroLogix. So you want to make sure that if you decide that you want to go to a larger slick system, that you go ahead and budget in the RS Logix 500. That might seem like a lot of money to you, but reality is, because if you buy the RS Logix 500 software, it covers the full line. All the MicroLogix and all the Slick 500 units are all covered in the RS Logix 500 software. So you have one common package that can solve a lot of your control needs, and you don't have to train a lot of different people on different software packages. The Slick 500 series, again, it uses the RS Logix 500 software. Then you have the larger PLC 5. The PLC 5 is really an antiquated system. It was in its heyday, it was the power horse. I mean, it was a powerhouse. It really had a lot of capability, and there was a lot of neat cards and what have you. The RS Logix 5 system is the software you have to use, and it also cost about $1,800. Really, you don't use these PLC 5s anymore. You might see them in some old plants, but rarely does anybody ever build a brand new plant and put in a PLC 5. The compact control Logix, this is a fairly new system. It uses the RS Logix 5000, and that RS Logix 5000 is extremely expensive. It's $5,900 for the complete package. The compact Logix control Logix system is very similar in size to the AB 1500. But its communications and speed and what have you are very, very fast, and has a lot of different options that you can use. Once you understand how to program the RS Logix 500, it's not a big jump to go to the 5 or the 5000. You'll understand it's all laid out about the same. There's just slightly different things about it. But that's the nice thing, is once you do understand the 500, you can jump to the 5 or the 5000 relatively easily. The control Logix is about the size of a Slick 500 system. It has a tremendous amount of communication options, and it does require the RS Logix 5000 software. Then you also have the Process Logix, which is also uses the RS Logix 5000 software. The nice thing about these different RS Logix or Allen Bradley options is they do use common software packages throughout the lines. Whereas if you were to use a Siemens S7 200, 300, or 400, you learn the S7 200, And then you jump to the S7300, and it's so different that it's like you're learning a whole new software package. And then if you jump to the S7400, it again is so different that you don't, it's not even the same at all. So that's the one drawback. Whereas the RS Logix packages, if you jump from one package to the other, it's very similar. A Flex Logic, the Flex Logix uses the RS Logix 5000 as well, and it's 5.9 K for the complete package. Safety controllers, guard PLCs 1200 and 2000. The reason I even mentioned this is we're not really going to touch on it, but there are safety issues when you're dealing with control systems. One of the biggest safety issues is the local emergency stop. So you see that large red push button on a control panel. That large red push button should never be wired solely to the PLC. It needs to be hardwired outside of the PLC. So when somebody hits it, it's going to knock all the output power off the output of the PLC, or even shunt trip a breaker if you would like. Some people like to go ahead and just knock all the outputs out, physically off the switch itself, and then in addition send a separate signal to the input of the PLC to tell the operator what has happened, that the local emergency stop has been pressed. But the important thing here is anything that can be used to cut, chop, or turn, or actually can cause a fatality, it can really kill a human being, is considered a safety issue, and they have to be controlled with safety PLCs, the Guard PLC 1200 and 2000. You can tell these are safety systems because they're orange. The Control Logix PLC does have a safety integrity level of 2. That's how they base safety systems, so you have different safety integrity levels. You'll hear it as seal levels, seal 1, seal 2, seal 0. That is a safety integrity level. And it's a whole unique way of programming. It's a whole unique way of understanding how the safety system works, and it's not recommended. Anytime you run into a safety system, it's probably a better idea to go ahead and use relay logic or different type seal rated relays or PLCs. So in this example, a Guard PLC is a seal level 3. A Control Logix PLC with the special software is a seal level 2. And all the other ones are seal level 0s. They're not to be used for safety. To cover all of the above PLCs in any detail would be beyond the scope of this course. Typical applications can be solved with the AB Micrologix or the SLIC 500 series PLCs. So that's what we're going to do, is we're going to use the AB Micrologix and the SLIC, this RS Logix 500 to solve these different applications. So here we have identifying the SLIC 500 system components. The above picture illustrates a typical SLIC 500 rack system. So here's the actual rack. You've got your power supply, you've got your CPU, and you've got your I/O. Here's a picture of the actual power supply right here. There's your CPU, fits in this rack, or this slot. Then you've got 2 input cards and an output card. These are your I/O modules. So this is a 4-slot rack. This is the chassis or rack. And then you've got your CPU slides into slot 0. It's the only slot it can go in. Then you've got your input 1, or slot 1, slot 2, slot 3. The processors in a SLIC system, you can have a 501 processor, a 502 processor, a 503 processor, and a 504 and a 505 processor. The 501 and the 502 are somewhat antiquated. The 503 uses the full gamut of different instructions. It has 2 serial ports. The 504 has a serial port, and also it has a Data Highway Plus port, which is for an industrial process network. Then the 505 has a serial port and an Ethernet port. This is a very easy processor to connect to a computer system. Processor types determine the following: the memory capacity, the complexity of the available instruction set, the communication options, and the scan time. The chassis or the rack. Chassis which house the processor and I/O modules are available in 4 sizes. You have the 4 slot, the 7 slot, the 10 slot, and the 13 slot. Additional chassis can be connected together to increase the I/O available to a processor. So here in this example we have 2 4-slot racks connected together with a cable. The maximum slots you can have in a SLC 500 system is 30 slots. So here you can see you have to have 2 power supplies, one for each rack. You've got a CPU, then you've got an input card, and an output card. And then on the next rack, this is rack 0, this is rack 1. So here you have another input card, another input card, and another input card, and then an output card. So if you were going to determine what slots these are, this is slot 0, slot 1, slot 2, slot 3, slot 4, slot 5, slot 6, and slot 7. So 2 8-slot racks and you can actually have 7 I/O cards in them. And then the first or slot 0 is reserved for the CPU. Power supplies, there are 3 AC and 1 DC power supplies are available. On the AC power supplies, they're typically 120 volt AC or 240 volt AC inputs, and there's a small little pin that you move around to select the different voltages. So on the first one, you have a 2 amp at 5 volts DC, 5 amps at 5 volts DC is the second one, and the third one is 10 amps at 5 volts DC. On the DC options, you have 3.6 amps at 5 volts DC. So on the DC power supply, you would power that up with 24 volts DC. This is a sample of an input module. This is a 16-bit input module, such as a 1746-IB16. So here, you've got, on this side, you've got your input. It's a 24-volt DC input. Goes into input 2. Whenever this switch is closed, the corresponding LED would be turned on. This is in slot 1. And then you've got your DC commons on the end, and you've got them tied to the negative of the 24-volt DC power supply. So when you're looking inside the PLC trying to determine the actual address of this input, this is I for input. It's an input module. This is slot 1, because it's in slot 1. And this is input 2. So it's I:1/2. If this was changed to slot 5, then this address would become I:5/2. So in this example, we have a new input card. It's put into slot 5, and we want you to guess what is the address of this connection. So again, it's an input module, so that's an I:, what slot is it? Slot 5, so that's I:5 / what input? Input 6, so that's I:5/6. I for input. The XX here is slot 5 / input 6. Here's an output module. What is the address of this connection? What size rack would we need? That's the question. So here you have this output module. They've connected 24 volts DC to the DC COM. And then you've got an output module here. So basically what's going to happen is this 24 volts DC is going to be put on this side of the coil. So you need the common of the 24 volt DC to be connected on this side. So whenever this is told to turn on inside the PLC, the corresponding light would turn on, and then the CR1 would turn on. But again, what is the address of this connection? So we have, what is this first one? It's an output, so that's O:, slot. What slot? It's slot 9. What bit? 1. So the address would be O:9 1. And the rack size here, we said, oh, well, because it's 9 slots, you could get a 10-slot rack to solve that, or you could get multiples of smaller racks to solve this as well. A 10-slot or 13-slot would definitely be a solution, or two 7-slot racks, or one 4-slot and one 7-slot rack. There's a lot of different combinations there to come up with this different, this output module in slot 9. So again, that's an output module, so that's O, :9, slot 9, /1, bit 1. And again, if this 24 volts is sitting here all the time, and whenever this corresponding PLC program turns on out 1, that relay will turn on. There's different SLC 500 I/O modules. You have your discrete, which is your input and output modules. You have your analog signals. You can have 4 to 20 or 0 to 5 or 0 to 10. You have high-speed counter inputs if you wanted to count a pulsing signal. You have stepper counters, servo positioners, communication, special communication I/O, and then remote I/O modules as well. A typical SLC 500 system, all the hardware, not including the software, can range in cost from $2,000 to $12,000 or even higher. If you've got a lot of communication cards in there, those can get rather expensive. Identifying micrologic system components. The micrologic PLCs are broken down into 4 distinct systems. You have your AB1000 micrologics, that's a fixed I/O. Your AB1100 micrologics is expandable I/O. The AB1200 micrologics is also expandable I/O. And the AB1500 micrologics is expandable I/O. On the 1200, you can expand it out to, I believe, 128 I/O. On your 1500 micrologics, you can expand it out to 256 I/O. AB micrologic line of PLCs are very powerful and inexpensive PLCs with cost-effective software. All micro PLCs are similar: GE, Siemens, AB, etc. And the AB appears to be more rugged, in my opinion. In this example down here, this picture, we have a Siemens S7200. It's controlling pumps, drives, lights, looking at photo sensors, and looking at push buttons. So in this example, we would need at least a PLC that could have 3 outputs and 2 inputs. This is a picture of an AB1200, a smaller module. And when you look at this module, you'll see this is where the port is, the main port. You can plug your PC into it, or an OIT, a terminal, an operator interface terminal. You've got 2 potentiometers here. You can actually use these potentiometers for field adjustments. There's a small button right here that if it's pressed, it'll change the communications of this port to the default communications, which is a DF1. The neat thing about these micrologics here are they can turn port 5, or that main port, into a Modbus communication port. You've got all your input lights and your output lights here, and you've got removable terminals here on the larger system, so you can actually pull these terminals out, replace the PLC, and snap them back in without actually rewiring. When you add the additional I/O modules, you can plug into here. This gives you the status of the processor. You can put a memory module right here, and these are the status of the outputs. And this is a DIN rail type system, so it snaps onto a DIN rail, and these tabs need to be pulled out to remove it. Again, the PLC looks at the process or a machine, determines the status of the process, and then makes decisions to control the process. So here you have your process. or your machine, and the inputs look at that process or machine. They make a decision. They send outputs to control that machine. This is a simplified block diagram of PLC and its components, the central processing unit, and the input and outputs of the I/O system. So a MicroLogix PLC by itself has all the inputs, has all the outputs, and it has a CPU. The unique thing about this is the main brick is always slot 0. So in this example, all the inputs are slot 0 and all the outputs are slot 0. A PLC input interface interprets the data from the input devices and then sends it to the CPU. The PLC's output interface interprets the data from the CPU and sends it to the output. So here you have input switches. Go to the input card or the input side of the PLC. They go to the PLC. They run through the software, and then the PLC sends signals to the outputs, which actually control the outputs. Signal flow through the PLC. In this example, you've got, again, your inputs, and then you've got your outputs over here, and then you've got internal logic in here. So if you can see here in this example, if 1 is pressed and 3 is closed, so that's closed right here, then if 1 is pressed, then this would be on. If 3 is closed and 2 is not pressed, it's open, then it's just going to latch itself on. So in Boolean functions, you can represent this as 1 ORed with not 2, ANDed with 3, and the function would be 7. Here we have 4 ORed with not 1, ANDed with 2, and then these two are, so it would be 4 plus 1 not 2 equals 8. And then the last line of code would be not 3 equals 9. Here's another example. You actually see your inputs here, 0, 1, 2. So if input 2 is on, then in the code it'll actually change states and 3 will turn on. So if input 2 is on, 3 will turn on and turn the light on. So that this is a limit switch like on a valve. What is a rung? A rung of ladder diagram code can contain both input and output instructions. The input instructions perform a comparison or test and set the rung state based on the outcome. Normally left justified on the rung. The inputs are left justified on the rung. The output are right justified on the rung. So in this example here you've got, this is called a rung because it looks like a ladder. So you've got the rails of the ladder and you've got a rung of the ladder. So you've got 2 inputs and then you've got your output. And that would be one rung of ladder logic code. An output instruction examines the rung state and executes some operation or function. In some cases, output instructions can set the rung state. Normally right justified on the rung. Series versus parallel operation. Ladder diagram input instructions perform logical ANDs and OR operations in an easy to understand format. If all input instructions in series must all be true for output to execute, that's an AND. If any input instruction in parallel is true, the output will execute an OR. That's an OR. So here you have A ORed with B, and this is ANDed with not C, D. So if you wrote this out, it would be if A ORed with B, ANDed with not C, and with D, then E equals 1, F equals 1, end if. Paralleling outputs allows multiple operations to occur based on the same input criteria. So you can actually put multiple outputs on the output of this rung by just putting a branch. These are actually branches. So when you do an OR statement, this is also a branch. So again, this looks like a ladder. You've got the rails of the ladder, and then you've got the different rungs where you would step on the ladder. That's why they call it ladder logic. This is your left power rung. This is your right power rung. And the direction of the way this is read is from left to right. Rungs of ladder diagram are solved from left to right and from top to bottom. Branches within rungs are solved top left to bottom right. So in this example, this is A ORed with B, ANDed with not D equals E, or F ANDed with a pulsing G equals set H. When you look at a pulsing or a one shot, basically whenever F closes, this guy will go, it'll toggle high and then it'll turn itself off. So H will just set, which means it'll latch itself in. So you can actually have fairly complex code in RS Logix or in ladder Logix programs that are not limited just to the Boolean identities. If you have a set or a latch, you must have a corresponding reset or unlatch signal. A normally open contact enables the rung to the right of the instruction if the rung to the left is enabled and underlying bit is set 1. So the way you draw this symbol is just a normally open contact. Looks like a contact off of a relay. A normally closed contact enables the rung to the right of the instruction if the rung to the left is enabled and underlying bit is reset 0. So again, this is a symbol for a normally closed contact. A positive transition contact or a one-shot relay enables the right side of the rung for one scan when the rung on the left side of the instruction is true. So on the left-hand side, if it becomes true, this positive transition contact will allow the output to turn on for one scan. Output coils, the referenced bit is reset when processor power is cycled. So the output coil, a symbol, looks like that little symbol right there, right here. Sets a bit when the rung is true, 1, and resets the bit when the rung is false. RS Logix 500 calls this an OTE, output enable. A latching coil is another type of output coil. Sets a bit 1 when the rung is true and does nothing when the rung is false. So here, whenever the input comes on, this will latch on and it'll stay on regardless of whatever the input does. It requires a corresponding unlatch. An unlatched coil would look like a regular coil with a U in it. So resets a bit 0 when the rung is true and does nothing when the rung is false. So whenever you have a latching coil, you need a corresponding unlatching coil. Here we have the Boolean identity A ORed with A and B equals A. So we're going to do this in ladder logic example. First we'll do a truth table. So we'll say A is ANDed with B, and that gives us the result Y. So 0, 0, 0, 1, 1, 0, 1, 1. And when you have to have both ones in, gives you a 1 out. Then we're going to OR that with our result Y. So A is ORed with Y. So 0, 0, 0, 1, 1, 0, 1, 1. Any one in gives you a 1 out. So when you draw this in ladder logic, A is ANDed with B, gives you a Y. Y is ORed with A, it gives you an F. So you can see in the Boolean identity 16, A ORed with A ANDed B truly does equal A, because it doesn't matter what B does, whatever A does here is the result. Here's another Boolean identity. We have A is ORed with B, ANDed with A is ORed with C. So here we have A ORed with B equals Y. A ORed with C equals Z. Then Y is ANDed with Z to give you F. And then you have A is ORed with B ANDed with C equals F. And technically these are both the same, but you can see the one on the right is much simpler than the one on the left. You can simplify it down to one line of code. You could also simplify the one on the left to one line of code if you just put those two on the same line of code. But I just broke it out so that it's easier for you to see. But it would look kind of silly if you had A is ANDed with A on the top one. In the RS Logix 500 software, you have data files. Data is divided into memory into data files. Data files are groups of the same type of data. So O or 0 is outputs, I is inputs, and that's not a 0, it's an O. So you have to put in O, not a 0. So O are outputs, I are inputs, S2 bits are your status bits. It's kind of like your housekeeping bits. Binary is your B3 bits. T4 is your timers. Counters are C5. R registers are your control registers, and integer registers are N7. So if you wanted to know the status of the battery in a PLC, you could actually look at one of the status bits and find out what the battery is. Is it low or is it having troubles or what have you? If you created an internal timer, you would use address T4 something, T4:0, T4:1, etc. If you used a counter, then you would call it a count. The first counter you used would be C5:0. Data is addressed by the data file and the location within the data file. Some processors include F8, which is a floating point data file. On the last one, that N7 integer value, it only displays an integer value, no decimal points. So if you wanted a real number or floating point number like 1.236, then you would have to use the address F8. Not all processors use floating point. The Allen Bradley 1200 does use floating point. Binary or integer data types. This is a raw binary data. The bits are grouped into words. The word address looks like B3:0 or N7:0. This refers to the first word of the data in the data file. These are 16-bit words, so you can actually look at each individual bit of the word. So if you wanted to look at the second bit of B3:0, the bit address looks like B3:0/1 or N7:0/1. This refers to the second bit of the first word of data in the data file. If you wanted to look at the first bit, it would be B3:0/0 or N7:0/0. Input and output data types. This data file contains the current status of the inputs. The word address is used for analogs. So here you've got a MicroLogix 1000. You've got the output module. It's one brick, so it's always slot 0. So it's out O:0 slot 0, the 4th bit. If you wanted to look at all the first inputs on this 20 input card, I:0.0 is a 16-bit word, so it goes from 0 to 15. Then you've got 4 additional bits. I:0.1 is the last 4 bits. The bit address is used for discretes. The location within the data file refers to the location of the I/O. So if we wanted to look, and here in this example again, it's O:0/4. If we wanted to look at this bit right here, we would say I:0/2. Status data types contains a variety of data concerning the current status of the processor. The data contained within this file varies by processor. Timer data types. The timer data type has a name such as T4:0. The timer contains several status bits. The enable bit, this tells you that the timer is running. The done bit, the timer is done. The timing bit, the timer is timing. The accumulated value, which contains the current accumulated value. And the preset value contains the value the timer must reach to be done. Counter data types. The counter data type has a name such as C5:0. The counter contains several status bits. You have C5:0, count up, it's enabled. Count down, the CD bit is the counter is counting down. The done bit is the counter is done. The accumulated bit contains the current accumulated value. The preset bit contains the value the counter must reach to be done. In a counter, the counter must be reset. So you can't actually stop. If you stop the counter, it's not going to go to 0. You must actually have a command that says reset that counter. Common instructions in the RS Logix 500 software. You have your time delay on, TON, and that's what it looks like. It can be used in all of the different MicroLogix and SLICs. And here you have your actual timer address, T4:0, your time base. This is 1/100th of a second. It's preset to 120, and its accumulated value is 0. So when it times out, the accumulated value will equal the preset value. And if you take this value and say 0.01 of a second, so that would be 1.2 second timer. The count up, the counter counts on a rung transition from false to true. The counter will continue to count even after the preset value is reached. The counter must be reset when you want to clear it. So in this example, you've got a count up, so it's CTU. It has a value C5:0. Preset is 120, accumulated value is 0, and it can be used in all of the modules. So when you use a counter, you've got to use address C5. If you use a timer, you've got to use the address T4. You can do mathematical functions in PLCs. There are a variety of functions available, and the processors that don't support floating point numbers, you lose precision. Some common functions are add, subtract, multiply, and divide. So you can see with a PLC, you're not restricted to the Boolean identities. You can actually do some fairly complex algorithms with an add function, or you can do simple, multiplication, division, etc. The only thing you need to watch out for is you need to make sure that you stay within a viable, you don't want to go over your maximum value. A compute function, this is a huge help when doing very many calculations, only supported in some processors. So you cannot use this in a 501, 502, or the fixed SLIC IO. However, you can use it in the AB1200. So you can see here you've got a compute function. Its destination is N7:36. They have an expression N7:13. N7:13 is ANDed with N7:14, which is ORed with N7:15. The results is stored in N7:36. A scale with parameters instruction. This is a very helpful, powerful command. As this chart illustrates, this command is only allowed in the SLIC 503 and above. This makes scaling extremely easy. And again, this can be used in the AB1200 as well. So in the scaling parameter, you've got this value, input N730. Its minimum value is 0. Its maximum value is 32,767. It's scaled from 0 to 10,000, and it's stored in N731. A scale data, this is an older type system. As the chart shows, this command is allowed in the 502 and above. This is a hassle because the rate and offset must be calculated. It's better than the alternative, the old 501 system, but the rate equals scaled max minus scaled min divided by input max minus input min. So you calculate these, and then you plug that value in as your rate. The offset equals the scaled min minus the, in parentheses, input min times the rate. So you have to do a little calculation before you get the properly linear signal out of this scale instruction. If your data changes, you have to actually go back and do your calculation again. You've got a compare instructions. Instruction is true when condition is met. There are many instructions with the same syntax. Equal is equal, not equal to, not equal. LES is the less than. The LEQ is the less than or equal. The GRT is a greater than. The GEQ is the greater than or equal. So you've got these different compare instructions that are used in all of the different processors. Open a project, navigate through a project. Configure the display, navigate through the help system, save a project. Using RS Logix 500, go through the menus and screens. So when you open up RS Logix 500, this is what you'll see this screen. So you can actually open up a project. So we'll open up test 3. If you want to copy that project, you just simply say File, Save As. You can save it as test 4 if you'd like. And opening a project is simple enough. You just File, Open. What you'll see is it's broken up into 2 different screens. There's also different screens up here as well that you can't see. You can actually turn those on so you can view the online tab, so you can see this portion of the screen came on. You can also turn on the tabbed instruction bar so you can actually change code from here. You can look at different projects here. You can open and close this file system here. So if you look at the help screen, you can actually look at the contents of the help screen. You can see the overview, the password protection, and you can actually carefully go through these and learn a lot more about RS Logix 500. You can actually search for specific items. Your controller, you've got your controller properties here. You'll first see that you've got your processor type, and here I've got this test processor configured for a MicroLogix 1200. It's Series C. It has 1 or 2 COM ports. If you buy a MicroLogix 1200-R, it'll come with 2 COM ports. One will be used for DH1, the other one can be used for any selectable item. You can actually turn the compiler off, or you cannot allow future access if you're trying to protect your intellectual rights. You can apply a password to your code. That way you can allow them to look at the code but not modify it, or etc. I prefer not to put in code, but some people will do it, and that keeps people from looking at your code and figuring out what you did. Then you've got your controller communications. The last configuration we did was a DF1, which we'll go over that in RS Links. You've got your processor status. You can actually see the S2 status bits here, and you can cycle through each one of those. You can also turn off these tabs, get a larger screen there. You've got your errors. If you have an error, one of these bits will change states, and you can determine what the error is. You can protect. If you can install your memory module, you can actually set these bits as well. So you can say, upon when memory module loaded on boot, whenever the unit is booted, it'll load the memory module. You can load the memory module on memory error, or you can load the memory module always. On power up, you can go to run mode, which is a good thing. Your math overflows. If you have a math error, these bits will change states. Then you've got a free running clock here. You've got your different functions. So here you've got a high-speed counter function. You can open that up and look at all the parameters there. On the 1200, you also have a TPI, which is the trim pot. So you can actually look at the values of the trim pot. We'll do that online. You can go through the rest of these. Your I/O configuration window. Here I have just a slick 1200 with no additional I/O, but you can add I/O, and you just would grab this card and just slide it over there, and you could add the I/O. Your channel configuration, you have channel 0 as DF1 full duplex. So you have your full duplex, but you could configure this for Modbus RTU slave or master, or even an ASCII port. And then if this thing had the R, see how it has 1762-L24XXXR. If it has the R controllers, then you'll have an additional port on the side, the left-hand side of the CPU, and this one is by default DF1 full duplex. So you can use this one for your programming port, and you can use channel 0 for whatever you wanted to use it for. You can see it's ID source 1. So that's your actual address of that port. In your program files, you have different ladders. So if you come into this ladder, you can see this is ladder 2. You can actually rename that and call that alarms if you wanted, or whatever you wanted to call it. And now you have a ladder called alarms. If you wanted to create a new subroutine, you just add it. It's ladder 3. Call it controls. And now you have a second ladder, which is like a subroutine, and it's empty at this point. And ladder 2 has something in it. And you can add up to, I'm not sure exactly how many, but quite a few. You have your actual data files. We talked about that. 0 or O is your outputs, I is your inputs, your status bits, your B3 binary bits, your T4 timer bits, your C5 counter bits, your control registers, your N7 integer values, and your F8 floating bits. So if we wanted to look at the values, we have two timers created, T4:0 and T4:1. And it gives you the time bases, the presets, the accumulated value, and the actual symbol. Counters, I've created one counter, C5:0. You can look at the N7 registers. We've got two registers created, N7:0 and 1. And the values that they currently have in them are 10 and 50. And then you got your floating point. It's come standard with one floating point address, F80, but if you wanted to create more addresses,